let me run through these with you really quick and then prove one or two of them. Maybe have you guys prove one or two of them too. So are you guys all comfortable with arc sine meaning inverse sine, arc cosine meaning inverse cosine, so on and so forth? And so these derivatives are all based on the idea that u is a function in terms of x, and a is some constant, whatever, 7, 26, 3, pi, whatever, some constant. Okay, so if that is the setup, then the derivative of arc sine, the ddx of cosine, is equal to u prime over, and does anybody remember the main feature of the denominator? There's a square root, yes. The square root of a squared minus u squared. There you go. So the numerator is u prime. It's the derivative of whatever u is. That's a chain rule factor, really. Divided by the square root of a squared minus u squared. You will see these presented a little bit differently. If you were looking in your book at 5.6 and 5.7, you'll see these presented a little bit differently what I'm going to show you here. Although I believe that what I'm showing you is a little more consistent when you look at 5.6 and 5.7 as a whole. This will flow a little bit better as we move into 5.7. Okay, and then the derivative of arc cosine of u over a. Any chance anyone remembers this one?
U prime a over...
No.
It's negative.
It's same as sine, just negative. That's right. So you can think of this as negative of u prime over the square root of a squared minus u squared. And hopefully that makes sense, because often the derivatives of sine and cosine are the same. They just differ by a plus or a minus. So hopefully that makes sense. So for that reason, very often, very frequently, this will not be part of like the AP framework just because of the ambiguity that you could see between arc sine and arc cosine's derivatives. Now, Colin, what about derivative of arctangent of u over a?
U prime a
Yep. Oops.
for
U prime times a
u
over this other stuff.
u plus a?
He's close, and she's saying squared, and
U squared plus a squared.
there we go. I think classically it's written as a squared plus u squared, but of course that makes no difference. You can obviously switch the order with addition. Those are these two right here, the ones that have not been circled in purple, the ones that have been circled in a lovely green color, those are your most frequently used derivatives of trig function, inverse trig function derivatives. And in each case, I will say that the chain rule factor is in place for all of these, so that u prime on all of them, that comes from the chain rule, really. So, for instance, if u is x, u prime would just be a 1, right? But if u is something more complicated than an x, then u prime would be something more complicated accordingly, with the chain rule. All right, so are these things that you need to memorize? I kind of think so. I think it would be immensely helpful if you just had this memory bank of, hey, I remember the derivative of this and the derivative of that. I'm going to show you how to do one or two of these, like how to actually derive the derivative. But when we get to 5.7, you're going to be like, oh, this is where it would be handy to like know the pattern and see this pattern without having to go back and reference something, because you won't have something to reference. So anyways, let's do one of these at least here. Let's see here. Yeah, it might be easier to learn how to derive these. I mean, that's highly debatable. I think it's best to memorize them. But if you forget if you forget one of them, maybe you won't forget how to find them. And that's kind of the point here. So which one do you guys want to do? You want to do arc sine, arc cosine, or arc tangent? Say again? Arc sine? Okay, fair enough. So here's how you derive the derivative of arc sine. So here's our goal. Our goal is to find the derivative of arc sine of u over a. And so we're going to set it up like this. We're going to set it up as an equation. We're going to say that y equals arc sine of u over a. So we could be a little more specific now and say that our goal is to find dy dx. Based on the way that I've set that up with y equals arc sine of u over a. If I could find dy dx, then I would have what I need. Okay, so step number 1. Anyone want to take a shot here? before you do that, actually, because if we could, if we just knew what the derivative of arcsine was, we're not really proving anything, right? Like, hey, I read this in a book, or my teacher told me this, whatever. Haven't really proved it yet, right? So we're trying to prove this. So I don't like this form.
I'm going to change the sign.
Change the
I'm
sign?
going to put the sign on the other side.
What if we did the sign of both sides?
That's right.
Okay. So what if it was sine of y equals sine of arcsine? Well, sine of arcsine just cancels, so you end up with u over a. This gets us to a different spot. So sine of y equals u over a. Remember, the goal is to find dy dx. Let's not forget that, because if we can find that, we're done. This is a better form, because I know what the derivative of sine is from previous work. So what do you think we should do? With respect to, that would be a bad move. Also be a bad move. What are we looking for? No, we're looking for dy dx, so I need to do, I don't need to do dy dx. ddx. ddx. So we've been talking about this a lot in AB. I know we talked about this a lot last year in AB as well. What that symbol means, ddx, is just shorthand for saying find the derivative with respect to x of whatever is showing up after this. So doing ddx means the derivative with respect to x of whatever you see coming up next. Okay, so what's ddx of sine of y? Cosine of y?
dy dx.
There you go. Chain rule factor would be dy dx. Agreed. So that's the left side. And there, hey, look, there's the thing we wanted. We wanted dy dx, and there it is. We didn't make it show up. It just showed up because we did ddx of something that had a y. Now, let's not forget this from before, that u is some function in terms of x. We don't really know what it is, but we know it's some function in terms of x. And the a is a constant. So that should affect how we handle the ddx of that right side. We don't really need to do a quotient rule, right? So what would you guys say the ddx of u over a would be? U prime over a, I can live with that. Or you could say du dx over a. I kind of like the u prime in this case, a little more compact, and we know that it means du dx. U prime over a. You guys okay with that? Basically doing a constant multiple rule. Okay, so now let's think about what I told you a minute ago about what this is. And we're trying to find dy dx. And you see some of the elements taking shape, right? You see the u prime. And there's an a in there, so maybe this is looking pretty good. I'm thinking we go dy dx. We just divide both sides by cosine of y. So it'd be u prime over a times cosine of y. And wow, look. It's almost there, right? Except instead of that square root thing, you've got cosine of y. That doesn't work. And we haven't really proved that the thing we said before is really the formula. We've got an extra a hanging out there. Any ideas on what we could do? Find the cosine of y. So you got to have an angle for that, right?
Yes.
Do we have any information about the angle?
Yes.
What? Yeah, all up here, right? This gives us information. That actually gave us information. I'm going to build a triangle based on that. So I'm going to look at this and say, well, sine of y, that means y is an angle, right? Just going to put it down in the lower left-hand corner. And what's the ratio for sine? Yeah, that's opposite over hypotenuse. So it would be u is opposite, a is hypotenuse. This isn't too bad. All I got to do is the cosine of that angle. The only problem is I got a blank spot for that side, right? Because I got to do adjacent over hypotenuse. How do I find whatever that missing side is?
A squared equals u.
Pythagorean theorem. Yay, there we go. And that's what you were describing, of course. So I think this ends up being the square root of a squared minus u squared, doesn't it? Pretty predictable based on what you know about what this should be. So now what I can do is I can replace cosine of y with adjacent, wait for it, over hypotenuse. Look how beautifully this is going to work out. This a would cancel with that a. Beautiful, isn't it? Right? And so then we've got exactly what we were looking for, equals u prime over square root of a squared minus u squared. And that would be our derivative with respect to x of arc sine of u over a. We would do a similar process for the derivative of arc cosine or arc secant or arc cosecant or arc tangent or any of them, right? We have a fairly similar process on all of them. This is just an example of one of them, and I feel like if you've seen it, they all have the same elements, right? You're going to have to do some trig work, you're going to have to do some triangle and some basic implicit differentiation to get there. Guys have any questions? So one of the questions that often comes up is, hey, are we going to have to do that? It's kind of the wrong question. I think you should be able to do all the mechanics of that. That shouldn't be an issue. What's the point of me showing this to you? I want to make sure that if you somehow space out the formulas and you got like 9 minutes left on some test and you're like, oh my goodness, I forgot the derivative of arctangent, you can figure it out, right? Using the concept that you see up there. We good? Questions, comments, concerns? Okay, so then what follows this is just some really basic, fairly easy practice, fairly easy for you guys, just because you have it together as far as how to use formulas and patterns and all that stuff. If you guys would please try numbers 1, 2, 3. Okay, here we go. So for number 1, you'd want to recognize that the input for arcsine is really 2x over 1. Maybe extend those parentheses down there just to make sure you can clearly identify your u and your a. Somehow you communicated with that one look. It's frozen. I could tell. Yeah. There we go. After a whole year, we're starting to speak the same language. That's good. That's good. Okay, so you clearly can identify, hopefully, your u as being 2x, and your a would be 1. And so then the derivative of arcsine, hopefully you'd call in the formula, right? You'd say, all right, the numerator is just a u prime. So it would be 2 over the square root. It would be 1 minus 4x squared. Good? We all agree? Okay. So then number 2, the derivative of arctangent of 3x over 5. Again, your u is right there. Your a is right there. And so you'd say for this, in the numerator, it's always u prime times a. It's a little bit different with the arctangent. So it'd be 15 in the numerator, divided by a squared, which is 25, plus u squared, which is 9x squared. Again, it's one of those rare times, just one of a handful of times where it's like, if you know the formula, you just drop in there and do some brief algebra and you're done. Okay.
You not even need to show the formula to get the points?
Yeah. Nope, if you can just apply it real quick and do the appropriate squaring, you're in good shape. Yeah, deriving derivatives, always a good plan. Thank you. Any other questions? All right, so then finally number 3 before we move on. This one, obviously a little bit more to it. You'd maybe do a little rewrite and say this is really ddx of arc cosine of x to the 1/2. Obviously, you can do that mentally as well. Not too bad. So recall that arc cosine is just exactly the same as arc sine, except the result is the other sign. It's opposite. So it'd be the negative of u prime would be 1/2 x to the negative 1/2 divided by square root of a squared, which is 1, minus u squared, which is x. A lot of simplifying that could be done there. And if this were some multiple choice, then it would be needed. But at this point, not totally needed. Anybody want to see some of the simplification that can be done? Anybody do anything? There you go. Okay. Yeah, so here's what Jeff did. He said it's negative 1 over square root of x times square root of 1 minus x, right?
Yeah.
That's essentially what you had? Oh, the 2. You have the 2 down there?
Yeah.
Okay. What do you guys think of Jeff's simplification? Good? Could go a little bit more. Sure. So couldn't you multiply this times this?
Yeah.
So you could say, all right, well, that's negative 1 over 2 times the square root of x minus x squared.
What if you're really fancy? You could make the negative outside.
What else? Yeah, you could. There's something else you could do. I don't know why you do this. Couldn't you move the 2 in there?
Yeah.
Would it become a 4 inside? If you wanted to, you could go -1, 4x minus 4x squared. I don't know. There's no rule that says you got to stop here. That's one spot you could go to. And if you wanted to, you could say plus 7 minus 7, just to make it more interesting.
And then do e to the ln of all, right?
Yes, there we go.
Why not do the integral of the derivative of that?
We could. We might get ourselves in trouble, but
Something inside to the -1.
there we go. We could make a real mess of this when it should have been simple.
Wait, if you actually added
Okay, Jasmine, go.
Can we actually write like plus 7 minus 7 in the test?
Yeah. You don't want to necessarily be known as that person, though. Like, no, honestly, like if you have some, like let's say it's FRQ 2 and A, part A. Let's say like the official answer is pi. Like that's what we're looking for. There's obviously some steps leading up to that. And somebody puts pi plus 7 minus 7, that's full credit. And as Josh eloquently pointed out, if you wanted to, you could write e to the natural log of all that. And that would still be correct. And any one of a number of crazy manipulations, as long as you didn't mess it up, which could happen, you just, at that point, just be trying to entertain yourself, which, watch out, right? It might go bad. So, whatever. Yes, Jake?
If at the beginning of the test you identified the term doink point as like a cusp or something, if you identified that at the beginning, could you?
If you use the definition of the derivative, like one-sided definition derivative, and you defined a doink point as that, why not?
Yeah, you like made like a
Just-
glossary and you were like joint point equals critical point and like defined critical or like inflection point.
You know what they're going to say? They're going to say, this test was way too easy because this kid had way too much time on their hands
Yeah, well,
with a glossary of alternative notations and words and... That would be, like, make sure, though, that you, like, direct them back to that glossary, because if you just throw things out there like that and you don't direct them back to the glossary, how are they going to know what to look at, right? Yeah, page 92, towards the bottom of the page. Wow. Yes, that... I've included some colored tabs for your thumbing through enjoyment. Yes. Okay. After you see 5.7, you'll probably be less inclined to dream these things up because you realize time will be a factor. So here we go. Just a little note here. These integrals up to this point, you'd have had to honestly look at them and say, I don't know how to do it. It's impossible. You would exhaust all of your skills and just you wouldn't have a conclusion. As I mentioned before, the key is basically what we did in 5.6. So if you can remember that and recognize the pattern based on that, we'll be able to see that the integral will lead you to an inverse trig function. We'll be focusing specifically on arctangents and arcsines. And this is a kind of a nice transition because we get into chapter 8, we're going to keep building on these skills. And we're going to build some other things in. Be a nice way to kind of compare and contrast the different things that will show up. So here's the idea. If you saw something like this, the hope is that you'd be like, okay, u prime, oh, there's a square root down there, and it's some constant minus some function being squared. And you'd hopefully arrive at the idea. I've seen that before. I know that that is the derivative of what? Arcsine. So as long as the u prime... Oh, you know what?
Negative arc cos.
Hold on. Sorry. I'll leave this as is. This is actually okay notation. You could go with that, but unfortunately if you did, you wouldn't see, if it was like multiple choice, you wouldn't see any of those show up as negative arc cosine. So you'd have to go back to the conventional arcsine. So guys, hey listen, as long as your u prime du is the right u prime du, in other words, like Timmy didn't mess it up, the u substitution pattern works, this would give you arcsine of whatever u is over whatever a is plus c. And then secondarily, if you came up to that next one, you'd hopefully look at that and be like, wow, it's a fraction. And you'd look through and you'd say, well, does ln work? And you'd ask these questions. You'd eventually arrive at the idea, well, maybe it's arctangent. And you'd be like, this is the arctan idea, the arctan pattern. It's u prime a over a squared. If this is derivative of arctan, and you would arrive at this right here. So a lot of this really is based on recognition and understanding how the chain rule works with these antiderivatives. So in order to get good at this, you have to see a lot of the derivatives, right, so that you can get used to those. In any case, though, I must say, you can always check your antiderivatives, right? As long as you know how to differentiate, you can always go back and check. The hard part is, this is a little circular, because if you didn't know your derivatives of arcsine and arctangent well enough, you're probably going to guess maybe the wrong thing, and then if you don't know how to differentiate those anyways, how are you supposed to check? So it is sort of a circular thing where, like, we just need everything to work nicely, as opposed to, well, I never really got the whole derivative thing down, and so that's going to really affect your ability to find these antiderivatives, which is going to be sort of foundational as we move into Chapter 8. So anyway, so I'm thinking of Jeff, I'm thinking of Jaden. They've seen these things for all of like 15 minutes. The rest of you saw these for hours and hours last year. So for you guys, veterans, you just got to remember this, right? It's in there somewhere. That might take some effort for sure. I'm not saying that that'll be easy. Jeff and Jaden, you want to take the time to make sure that you understand the patterns of the derivatives of arcsine and arctangent, so that as we get into these integrals, the antiderivatives, it won't be too hard for you to be able to recognize the patterns going the other way. Does that make sense? All right. So a nice example would be something like number 1. And I want to go through this with you. This might be a little painful. I hope it's not too bad. But I always like to think of you guys doing a quiz or a test and thinking, what would they think about this? So let's run through the possibilities. This is kind of the pattern of thinking that I'd like to suggest to you all as you attack these. So step 1, let's just say this is like number 19 on some quiz in 2 months. How are you supposed to know that it's leading to some inverse trig function? That makes sense? Y'all do just fine when it's like, hey, here's a block of arcsines. Here's a block of arctangents. You get into this math robot mode and you just go arctangent of this, arcsine of that. But if this is out of context, how do you know? So here would be what I would suggest. Number 1, you got to recognize that this is an integrand that is a fraction. And here's the ordering that I personally like. I advocate this simply because this is what I like. You can go in a different order than you want. I have my reasons for this, but you can flip the order if you would like. The first thing I ask myself is this going to lead me to some kind of a natural log? And let's remember that the natural log pattern is the integral of u prime over u. Right? You remember that from the 5-1, whenever that was? Last week sometime? So essentially what we've got to ask ourselves is the derivative of the entire denominator either equivalent to the numerator or only off by like a minor factor of like 7 or 8? In other words, Timmy messed up. So let's think this through. What is the derivative of the denominator? It's kind of a mess, isn't it? It's 1/2 times 4 minus x squared to the negative 1/2 times negative 2x. So you got to ask yourself, maybe you do this mentally, but you got to ask yourself, is that the numerator? Yeah, Timmy really blew this one up, right? It's way off. It's not even close. I'm asking essentially, is this the same as that? Clearly, we're off by a little, right? We're off by a lot. So that doesn't tell me that I need to figure out how Timmy messed this one up. I got to come to the conclusion that it's not ln as a result. Make sense? I'm asking myself, is the derivative of the bottom and the top? That's the derivative of the bottom, and I compare that to the top being 1. It's not the derivative, and it's not even close, right? So I gotta say, you know what? It's not natural log. It's none of that stuff. So I'll just erase this. I'm just doing this kind of in my head, some of this at least. Okay, so I move on. The next thing I want to ask myself is this a flip up? I'm trying to give you guys an organized way of approaching this instead of just random shots in the dark and hoping that if you hit something, it's organized. So flip up would mean integral of 4 minus x squared to the negative 1/2 dx. Now this is composite, right? For this to work, the derivative of the inside has to be the other factor. So what's the derivative of the inside? Negative 2x. And what's the other factor in the integrand? It doesn't seem like there is one, right? So the other factor would technically be 1. Technically, it's 1 times that. So the derivative of the inside is negative 2x. The other factor is 1. We're off by a factor of negative 2, which is no big deal. We can fix that. But the fact that we're off by a factor of x tells me that we have the wrong pattern. Let's not flip up. I can't flip this up. So that's out. Which at this point in the game, here in about a week, we'll have alternatives to this. But at this point, this has me thinking, all right, well then it has to be arcsine, or arctangent. Those would be my other possibilities here.
Would you just never assume arccosine?
Yeah, like arccosine is sort of like the awkward uncle at the party that no one wants to claim. It's there, but we never use it, really. I think you might find it show up on some test prep booklets every now and then, but I don't think you'll see it show up. Yeah. Okay, so based on the form of that, would you guys say it's arcsine or arctangent? It's got to be arcsine. What told you that, Josiah? Square root tells you all you need to know. And it does have the right pattern within there. So we're going to assume intelligently for the moment. We have a reason for this. We're going to assume that it's arcsine. So if it's going to be arcsine, what would the U have to be for it to fit? U would have to be X, and A would have to be 2. Okay, so then U prime in this case would be 1. And you think back, okay, if it's going to be arcsine, it's going to have to be U prime over the square root of A squared minus U squared. It comes down to this. Is the U prime the right U prime?
Yes.
Of course it is. So this one has not been messed up by Timmy or anyone else. So we end up with arcsine of X over 2. And then don't forget the plus C is still there even though it's arcsine. What do you guys think?
Good job, team.
Yes, Timmy did not mess up for a change. Maybe that conversation we had the other day inspired him to do a little better. Any questions? Okay, so then we're going to move on to some other ones. So number 2. Don't assume stuff. These can be totally different than you think based on one little detail. So don't assume anything. Let's go ahead and go through. Let's ask ourselves, is it natural log? Oops. So natural log, what are you testing out with natural log? And the derivative of the bottom is? Not the top. And more importantly, we're off by a factor of x, aren't we? So it's not ln. Is it flip up? Why is it not flip up? Again, yeah, we're off by a factor of x. So we're left with arcsine or arctangent at this point. Of those two, if it's only down to those two, which would it have to be? It's got to be arctan. Okay, so if it's going to be arctan, what would my u have to be here? 3x. And my a would have to be 2. So this one, did Timmy mess up? He totally did. He totally did because u prime is 3. And remember for arctan, the numerator is supposed to be u prime times a, which would be 6. And you look at the numerator, it's just 1 times dx. It should be 6 dx. I'm going to multiply by 6, meaning I've got to multiply the outside by 1/6, leaving me with 1/6 arctangent of u over a, 3x over 2 plus c. Just to show you how different these could be, even though they look very similar. Does anybody know what this would lead to? Let's try it. That'd be flip up, right? Derivative of the inside is 2x. The other factor is x. So Timmy messed up, but not that bad, right? Only by a factor of 2. So I fix it, the 2 and the 1/2 factors. So it'd be 1/2. This just goes back inside. But now is when we run into issues, don't we?
Are you sure it's not 18?
Oh, darn it. It doesn't matter either way. You're right. There's our 18 right there. Sorry. Why is it not going to matter? Yeah, you add 1 to the -1, you get a 0. You have to divide by 0. And anytime you find yourself dividing by 0 with an integral, it's probably going to lead you back to natural log. So this is definitely a natural log. Here's how you'd get there. I think you should not be skipping any of the steps along the way. I think you should be asking yourself right away, hey, it's a fraction. Is the derivative of the bottom the top? And the derivative of the bottom is 18x. So if I just fix that, then I've got an exact chain rule for natural log. So give me 1/18 natural log absolute value of 4 plus 9x squared. Absolute value is a little redundant there. We don't have to have it because of the 4 plus 9x squared, regardless. So let's be honest. The only thing I changed is I threw an extra x in the numerator. That turned it in from being an arctan over to an ln. So be very, very careful with these. They can be tricky if you're not paying attention to all the little details. Okay, so then we got a few more here. If you guys would please try numbers 3 and 4. And we'll tackle 5 and 6 later. Let's do 3 and 4 right now. Tricky. The degrees seem a little bit messed up. So again, I don't know. I don't think I'm just like wasting time here. I really don't. I think you should always consider natural log first. Let me just give you a preview, actually. So when we get into Chapter 8, our next unit, we'll do this a little on Thursday. We'll do this a lot in the coming weeks. You're going to get stuff that is all jumbled up. It's not going to be, hey, this is from the arctangent section, this is from the ln section. Things are going to be all over the place, and you're going to have to investigate. Is it this, is it that? And some of them are really easy. Some of them are far more difficult. And so you want to get into this mode of investigating, not just like the, hey, Mr. Anderson, it's in the arcsine chapter, so it's going to be arcsine. It's the wrong attitude. Make sure you're going through this. Why is it not ln?
Because you're off by a factor of x.
Yeah, what would the numerator need to be? X cubed or some 4x cubed, 10x cubed, 20x cubed, something x cubed. That's not what it is. So it's not ln. And really, as far as flip up goes, similar reasoning in addition to the whole dividing by zero thing. It's not flip up. And so if it's going to be arcsine or arctangent, which one does it have to be? Because there's no what? Square root, and also it's plus instead of minus, and the order is even wrong. So there'd be a lot of reasons why it couldn't be arcsine. It's got to be arctangent. Your u would have to actually be x squared. Your a would have to be 5. Your u prime would be 2x. So this will fit. However, we have a major issue with Timmy and his messing up. What would the numerator need to be? It needs to be u prime times a, which would be 10x, right? U prime a for arctangent. So we need to multiply the top by 10 and the outside by 1/10 in order for this to actually fit the pattern. So this would be, for a final antiderivative, 1/10 arctangent of x squared over 5 plus c. What do you guys think? Okay. Then number 4. Again, let's just run through why it's not natural log. Any ideas? The root is a major issue, for sure. And then even if you ignored the root, aren't we still off by a factor of t? I mean, there's a couple reasons, not ln. Flip up, you're going to be off by a factor of t. And so we're left with either arcsine or arctangent. Which one does it have to be if it's one of those two? It's got to be arcsine because of the square root. So then that would mean u would have to be 4t, a would have to be 3, u prime would be 4. Remember the pattern for arcsine? Bless you. The numerator has to be u prime. Bless you. So that means the numerator has to be 4, and it's a 1. So Timmy messed up. We can fix that. Times 4 times 1/4. So it'd be 1/4 arcsine of 4t over 3 plus c. Any questions on those two? Okay, so our final two examples of the day and the chapter are 5 and 6. Okay, so 5 and 6, again, I want to take you through this, especially 5. 5 is pretty devious, and you're going to find when you get into chapter 8 that there are going to be questions that look really, really similar to that, but the thing I'm about to show you doesn't even work. It's going to be hard to differentiate between the two. I'm going to give you some ideas about how you could do that. But you want to be very systematic and organized about the way you approach this. So tell me, on number 5, why can we just immediately dismiss ln as a possibility?
Because there's no x on the...
Yeah, and wouldn't the derivative of the bottom be 2 whole terms? It'd be 2x plus 6. The numerator is a single term. I mean, There's a couple different reasons, but it's not ln for sure. Okay. Why is it not flip up? I think there's two ways you could think of this. Yeah. And also you'd get the whole division by 0 if you tried to flip up. So both reasons there. It's not flip up. So it's got to be arcsine, or it's got to be arctangent, or it's got to be that whoever wrote this question wrote a bad question. It's one of those three possibilities, because when you look up there, it definitely doesn't look like arcsine, right? Because there's no square root. But it didn't really look like arctangent either. Because remember, arctan is u prime a over a squared plus u squared. There's an extra term. So there it is, of course. The square root really disqualifies arcsine. But we might be able to take that and turn it into a nice arctan pattern by, what did you say?
Plus 9 plus
Perfect square. Say again?
plus 9 plus 25.
Yes, also known as complete the square. Yeah,
Oh, no, not complete.
that's what you got to do. So I'm going to just go off to maybe off the side here and say x squared plus 6x. Here's how you complete the square. Here are the steps. Step 1 is to group the first two terms. And you got to make sure that your a value is a positive 1. And it is. So that's not going to be a big deal here. It'll be a big deal later. So you got to group the first two terms. And I always leave a little bit of space. And if you remember from back in Algebra 1 or 2 or whatever it was, the way that you complete the square is you locate your b, and you take your b and you cut it in half and square it. So what is your b?
6.
Half it and square it gives you
9.
9. So what I'm going to do is I'm going to add 9 to the inside of the parentheses, but I got to keep this thing balanced. I can't just add 9 to something and call it the same thing. Subtract 9 from the outside. So if you look at the two red numbers there, what have I done to this expression?
Nothing.
Nothing. I've added 0. And from your properties, you know that if you add 0, you just get the same thing you started with. But it's a much better form. And so now, as I turn to a very lovely brown color, what remains is a factoring, which would be x plus 3 squared. And then, of course, 24 minus 9 is 25. So what I can then do is I can replace that denominator with that. And I think it'll look much better. I'll pull the 6 out here too. So it'd be 6 times the integral of 1 over 25 plus x plus 3 squared dx. I haven't changed the value at all. All I did was I added a really smart 0. But I've totally changed the form. Completely different form.
Oh, there's 6.
Yeah, I just brought the 6 out.
Found it.
So since we kind of presupposed that this was an arctangent, I need to identify my u. What would you guys say my u is? X plus 3. My a is 5. And my u prime would be 1. So in order for this really to be arctangent, the numerator has to be u prime times a. And u prime times a is 5. My numerator is just a 1. So I'm going to multiply that by 5 and divide the outside by 5. Fix Timmy's little mess up. This will lead me to my final antiderivative of 6/5 arctan of x plus 3 over 5. And then don't forget your plus c. So I heard a little groan when I said, complete the square. Right? I know that that's one of those things in algebra where it never seems to get easier. Maybe, I don't know. There it is. Got one last one to do here. So let's take a look at number 6. So number 6, maybe the first thing you do is you get the 7 out of there. So it would be 7 antiderivative of 1 over square root negative x squared plus 8x plus 9. But then you get into all the details here. So tell me, why is this not natural log?
There's no x and there has to be 2 terms.
And even the whole square root, I mean, there's lots of reasons. You've hit on a couple of good ones. It's definitely not natural log. Why is it not flip up? Sorry? Chain rule pattern is way wrong.
Yeah.
Right, that's the main thing, right? We need a negative 2x plus 8 is the other factor, and that's definitely not it. So it's not flip up. That leaves me with either arcsine or arctangent at this point. which one, if it's one of those, which one does it have to be? It's got to be arcsine. What's the main thing that tells you that it's arcsine? So the completing the square, right? Because this does not look perfectly arcsine to me. We got to complete the square to create that. So the completing the square is a little tougher. So I'm going to write this. I'll just come off to the side to do this. Negative x squared plus 8x plus 9. I'm going to group my first two terms. This is where this one gets tricky. In order to complete the square, your a value has to be specifically 1. And right now it's negative 1. How do I fix it? And I'm going to factor the negative out of only the first two terms. So it's going to be negative parentheses positive x squared minus 8x, leave a little space, plus 9. So now that the a value is positive 1, I can complete the square. So this is still the same, right? You find the b, you half it, and you square it, and what do you get?
16.
Positive or negative 16? Positive. Okay, so I agree. So I'm going to take that 16, and this is where this one gets really tricky. I'm going to go plus 16, and the tendency is to be like, oh, I added 16, but you really didn't just add 16. What did you really do? You really subtracted it. Don't forget that that 16 is inside the parentheses that has the negative on the front. So the truth is you subtracted 16 from this expression. So to balance that, you've got to add 16 to the outside. So it might look like I just added 32, but I didn't. I really just added 0. Just a smart 0. Okay, so the way this finishes is the factoring is x minus 4 squared, and then out here, of course, is plus 25. So to finish this off, I'll rewrite it like this. Bless you. Like so. You guys presuppose that this was arcsine. Totally agree. Let's figure out what our u would have to be. What do you guys think? U equals?
X minus 4.
Yep. That means the a has to be 5 and your u prime? It's 1. So the numerator is supposed to be u prime, and look, it is. Nobody messed up. And so this would finally end up going to 7, arcsine. Got it. And plus c. It's kind of hard to warn you about the stuff you don't know, the stuff you've never seen before. But please trust me, in Chapter 8, you'll be thankful that we went through all the steps to get to these points, because we're going to add some stuff in. Brandon?
Will these be on the test on Wednesday?
Tomorrow? Or 2 days from now?
Yes.
Definitely not.
Where does
The
that-
1 week from this Wednesday, yes.
So we just turn in the chapter 4 extra.
Just Chapter 4. Yep. Liz?
So what's like the last thing in chapter 4?
Trapezoid approximations, integrals by substitution.
So all stuff from last year?
Yep. And to be honest, Chapter 5 is all stuff from last year except for hyperbolic sine and cosine.
What chapter is this?
5.
Was this last year?
We did all this last year. At least I did.
No, these are mine.
I hope you did.
Did we do this last year?
Do what?
This?
Yeah, but I never understood.
Okay.
Are you doing okay now?
Yeah, I get it. Actually, can you go back to 5 real quick?
Sure.
I thought I got it, but then there was like Timmy messed up, wasn't he?
Timmy messed up a little bit, yeah. So it was 6 integral 1 over, let's see here, it was 25 plus x plus 3 squared, right?
Yeah.
Okay, so then I said u was x plus 3, a was 5, and u prime was 1. So to fit the arctan pattern, the numerator has to be u prime times a.
Oh, it's times 8. So that's
And yeah, so u prime times a would be 5. So we'd have to go times 5 divided by 5. Say again?
I just forgot.
Yeah, the a has, the tangent, arctangent has a on the top. So if you look in your book, you'll see all these formulas, like the one with arctan has like a 1 over a out front. That's like the Timmy messed up the chain rule adjustment.
So
So
when you're writing the arctan of, it's still just arctan over U prime or Q over A, right?
like when you get to your final answer?
Yeah.
Yeah,
You
yeah.
just have the x plus 3 over 5.
Right, yeah, so it'd be 6/5 arctangent. Yeah, no matter how complicated the U is, that's the U. So it'd be x plus 3 over the A, which is 5.
That makes sense.
Yep.
Thank you.
Yeah, you bet. Okay, so guys, next time I'll see you is Wednesday, no earlier than 7, so sometime after that, okay, for the test. All right, have a great rest of your day. See you then.